Hello, everyone. This is Group 1 presenting Digital Transmission in Free Space through a High-Power Laser. Group 1 being Alexander Simmons, Curtis Kane, Ivan Huang, Monica Castro-Suarez, our mentors being Dr. Wei, Dr. Carr, and our committee being Dr. Hawawin, Dr. Maddox, and Dr. Eikenberry.
For goals and objectives, our basic goals are to convert digital signals into optical pulses by developing a system for coded modulation and purchasing a laser with transistor logic circuitry and maximizing signal reception by developing an efficient optical system and selecting a photodiode that can accept 980 nanometers. The advanced goals are real-time decoding through developing a microcontroller system and integrating AI machine learning capabilities, and also optimizing signal transmission through simulating possible optical layouts of the best results and finding better lenses and mirrors. As for stretch goals, we would like to develop this project for off-grid emergency use by introducing bidirectionality and shrinking the system into a smaller portable form factor, and megabit transmissions by switching to a low frequency laser and integrating electro-optical components to increase the power of the laser and allow it to carry more data.
This is a brief video of the optical system driven by a square wave produced by the function generator. You can see here the flashing laser module in a continuous loop, our beam expander, culmination lens, then our horizontal and vertical adjustment mirrors, which then go into our focusing lens, hitting our detector head, connected to our receiver circuit. Then you can see on the output screen our high and low voltages showing the signal is being read. This is our optical diagram of the system shown in the previous video. You can see some big differences are that we're using a red laser instead of infrared and the lack of an optical filter. Due to shipping issues with the infrared laser, we had to change to a temporary 635 nanometer laser, but then also leave out the optical filter because the one we have is for 980 nanometers. Some basic info on the 635 nanometer laser and how it affected the testing in the demo. The 635 nanometer laser is also TTL, but it is also at a lower power than the infrared, being at about 5 milliwatts to 10 to 15 milliwatts of power, but it still was able to maintain the same modulation rate, allowing us to continue our testing. The lower also had a elliptical shape of the beam, which led to issues with a reduced signal right at the receiver, but it is compatible with existing and transmitter receiver circuits that we have.
This is a test of the laser over 20 feet. You can see as we start it here at the beginning, it's about a 1 by 2 millimeters in beam shape. Goes through beam expander, culmination lens, adjustment mirror. Over free space is about the halfway point. You can see significantly larger, about an inch. And we get over here to the receiver end with the focusing lens, still about an inch, 2 inch. And then you go into the focusing lens where it's adjustable, the hot spots, focusing lens right about there, should be pretty good.
And we will do more testing at longer ranges when the infrared laser arrives. This is our optical test using a function generator to input a continuous square wave signal at 1 Hz, which translated to the letter U in the binary alphabet shown here. And so because it was continuous and able to continue going from one to the other, we use this as our testing signal to ensure the receiver was accurately reading. Some future improvements and corrections to some remaining issues we had. Our elliptical beam shape and coupling efficiency, both of these can be fixed or reduced by the use of cylindrical lenses for correction and reshaping the beam into a circular profile. And next steps are essentially integrating the infrared laser when it arrives after the demo and resuming our testing and calibration at intended transmission distances for demonstration purposes and applying correctional optics if needed. Thank you.
A photonics-based specification we are measuring is the amount of power generated by an unfocused laser compared to a focused laser, which will help determine the amount of photocurrent generated by the photodiode and power lost in the optical system. The table here displays values for the power of the unfocused laser and power of the focused laser in 10 trials using a power meter and red laser. The highlighted values are demonstrated in the following live demos. The values from both columns are not linear due to fluctuations from the power meter and human error, but what is consistent is that a significant amount of laser power is lost, mostly due to atmospheric disturbances, lens and mirror defects, and beam divergence. The first two values shown here are averaged from values from the previous slide. The third value demonstrates the amount of power lost during transmission as a percentage, which is 69.4%. The fourth value shows the amount of photocurrent generated from the photodiode based on the focused laser power average and the photodiode's responsivity. To reduce power loss and maximize power reception of the photodiode, especially as will increase the distance of the setup, we will need to select optical elements with the appropriate diameters and focal lengths and reduce any background and physical disturbances. The following live demos of the measurements will be played.
Demo 1. Demo 2. Demo 3.
This is the start of the hardware design. This slide shows an overview of our hardware pipeline. It starts with a microcontroller that converts written text from the laptop to binary data that will be used to toggle the laser in a subsequent manner so that zeros will represent when it is off and ones will represent when it is on. The laser beam then travels through an optical path composed of lenses and mirrors for beam shaping and collimation. At the receiving end, a photodiode captures the signal, and the output current is converted to voltage using a transimpedance amplifier. Using the microcontroller's built-in analog-to-digital converter, the signal is then processed by the microcontroller, and its output is then sent to the LCD to be displayed. Using Fusion 360, we developed a detailed 3D CAD model of the physical system, including the PCB container, condensed component layout, and light optical mounting. Two additional views are zoomed in to show how components like the PCB and photodiode are positioned for alignment. Creating this model helped guide physical prototyping by verifying mechanical fit, optical paths, and wire routing in advance. This was our very first test of the photodiode receiver circuit using a modulated square wave input. At this point, the transimpedance amplifier was producing around 5 millivolts of output. While the signal was visible and showed expected waveform pattern, it was clear that the amplitude was still too low for reliable digital decoding.
This initial test was crucial. It confirmed that the system was functionally responding to light modulation, and it gave us a baseline to begin optimizing gain and sensitivity. In the second test video, we demonstrate the improved performance of our photodiode receiver circuit. Initially, the transimpedance amplifier was only outputting around 4 millivolts, which was too low for consistent signal decoding. After troubleshooting and circuit adjustments, we successfully increased the output to 9 millivolts. This demonstrates the sensitivity of our analog backend and validates our component selection, particularly the OPA381 transimpedance amplifier, and how it can reliably detect low-intensity light signals. This was our most recent test, where we successfully decoded the letter U using a faster cycle rate. By this point, we had significantly improved both the receiver sensitivity and the timing accuracy of our decoding algorithm. The signal was stable, and the system was able to correctly interpret the incoming binary sequence under real-time conditions.
2, 1. Software comparison. I am using the MSP430G2553 for testing and to implement onto our microcontroller. I tried 3 different softwares, Code Composer, Arduino IDE, and MicroPython, and chose Arduino IDE. Due to I am able to use C language as well as user-friendly, though its performance is medium compared to Code Composer, it still works well with me and what I need it to do. Though I still kind of flip over to Composer, I still kind of lean heavier on Arduino IDE. This is our software design flowchart, which outlines the structure used to develop our code. For this midterm checkpoint, I implemented a system where the user can implement a message, for example, hello, and the program converts it into binary. Each bit is then transmitted using the laser. 1 turns the laser on, and 0 turns it off. The laser beam travels into a photodiode receiver, which detects the signal and decodes the binary back into the original message, completing the communication cycle.
There you go. Watch the laser. Laser's gonna flicker in binary.
Yes and no. Because like you just gotta be smart about
Saying
like, if you're doing,
hello.
like some shit that has like all 5 colors, you just do like there's a setting on there that's like you bleed into infill. So anything that's infill, it'll do the filming change inside. You know what I mean? You try it.
And it's saying hello. There we are.
Really? One time I was
This is the code for a continuous stream of off and on, just continuously, which is the binary code for you, and what is it, 8 bits? And it goes through the control board, input, the laser flashing on and off, our stuff, mirrors, free space test, our photodiode, and then our receiver showing us continuous stream of views. Cycle rate is 0.01 seconds, printing out U continuously, flashing a little bit faster, going through, detect. This is the code doing a continuous stream of on and or off on, which is our U signal. It's going through there, flashing it on, and our output is a continuous stream of U's. So I think we're good.
So let's go here. Right now, this is extruded of 13.4 millimeters. So what number do you think would be best? Because we can put the camera in right now and see how much it protrudes by.